Welcome back, everyone, to the deep dive. Light and shadows. It seems like a pretty basic concept, right?
Sure, we all learn about it in elementary school.
But what if I told you that scientists have actually found a way for light to cast its own WN shadow?
Yeah, that's right. It sounds impossible. I mean, shadows are formed when something blocks light.
Exactly. It's mind-bending stuff.
But light itself?
It's light. So how can it be the thing doing the blocking? Well, we're diving deep into a recent scientific paper and some news articles that explore this wild idea.
And get this. Researchers at the University of Ottawa actually did an experiment to test this out, and they observed it happening.
Okay, so before we get lost in the how, let's just take a second and think about the what.
Good point.
I mean, we all learned about shadows back in grade school.
Right.
Something blocks light, a shadow is formed. But this is different. This is light itself. So are we actually talking about a shadow here?
Well, that's part of what makes this so interesting. It really challenges how we define a shadow.
So how are these researchers defining it?
Well, they're saying we should broaden our definition of a shadow based on what we can actually observe. So their criteria are if something moves with the light source, it's visible to the naked eye, and can be projected onto another object.
Okay, yeah.
Then it qualifies as a shadow, even if the object casting it is light itself.
So they're saying even if it's light, if it checks those three boxes, it can be called a shadow.
Yeah.
Okay, that's pretty wild.
It is.
So how did they actually do this in a lab? Like, how do you begin to test this idea?
So their experiment involved 2 lasers and a ruby cube.
Okay.
Now, ruby is key here because of its atomic structure. Think of it like this. Ruby has these energy levels, kind of like steps on a ladder.
Okay, so we've got our ruby and its atomic ladder. What about the lasers? Where do they come in?
Okay, so one laser, a green one, acted as the object that would cast the shadow.
Right.
When this green laser passed through the ruby, it energized those atoms in the ruby, bumping them up to a higher energy level, a higher step on that ladder.
Okay.
The other laser, a blue one, this provided the background illumination.
Got it. So the green laser is like giving those ruby atoms a boost of energy.
Yeah.
And the blue laser is like setting the stage, right?
Exactly. Now here's where it gets really interesting. Once those ruby atoms were all energized by the green laser, they became much more likely to absorb the blue light.
Okay.
And that absorption, which happened right in the path of the green laser, is what created the shadow.
So it's not that the green laser is like directly blocking the blue light.
Yeah.
It's more like it's using the ruby to do the blocking.
Yeah, that's a great way to put it. They actually observed this shadow projected onto a screen.
No way.
Yeah, there was a distinct dark area that mirrored the shape of the green laser beam. And get this, they could even see it with their naked eyes.
Whoa, wait. So they could actually see a laser beam casting a shadow.
Yeah.
That's incredible. But how do we know this is truly a shadow and not just some other weird optical effect? I mean, what makes it different?
That's a valid question, and the researchers actually thought about that too. They laid out 3 criteria that had to be met for this phenomenon to be classified as a shadow. First, it had to move with the green laser.
Okay, that makes sense.
And it did. Second, it had to be visible to the naked eye.
Which we already said it was, right?
Yep, check. And finally, it had to be capable of being projected onto other objects, just like a regular shadow.
Okay, so they really put it through the ringer, and it passed all the tests.
It did, all 3.
Wow, so it seems like it really is a shadow, even though it's created by light itself. I mean, that totally changes how we think about shadows, doesn't it?
It really does.
But I'm still a little stuck on how this is even possible. What's the science behind this? Like, how can a laser, which is pure light, create darkness?
Well, that's where we get into the world of nonlinear optics. So remember those ruby atoms and those energy levels?
Yeah.
In a linear system, if you increase the intensity of the light, the effect on the material increases proportionally. But in nonlinear optics, things get a little weird. Well, imagine you're shining a flashlight on a wall. The brighter the flashlight, the brighter the spot on the wall, right?
Yeah, makes sense.
That's linear.
Okay.
But with nonlinear optics, things aren't so straightforward. If you double the intensity of the light, the effect might not just double. It could triple or even increase tenfold. The response isn't proportional.
Wow. So it's like the ruby is reacting to the green laser in a way that's not just a simple one-to-one relationship.
Yeah, you got it.
That's really interesting.
Yeah, and that's actually key to understanding how the shadow is created. The green laser by exciting those ruby atoms, triggers this nonlinear response where they suddenly get really good at absorbing the blue light.
Okay, so it's this amplified absorption that makes the shadow possible.
Right.
We've got light messing with matter on an atomic level to create a shadow.
It is pretty incredible when you think about it like that.
So is this shadow just like a fleeting thing, or can we actually measure it? What do we know about its characteristics?
Oh, it's definitely measurable. The researchers actually did a quantitative analysis of the shadow. They looked at its darkness, which we call contrast, and its shape.
Okay.
And they found that as they increased the power of the green laser, the contrast of the shadow increased too. Meaning it got darker.
Yeah.
Just like a regular shadow gets darker with a stronger light source.
Okay, that makes sense. What about the shape? Did the shadow actually look like the green laser beam, or did it get distorted somehow?
Well, this is another really cool thing. The shape of the shadow exactly matched the shape of the green laser beam. So that confirms that the green laser was directly responsible for blocking the blue light.
Wow. So we've got a laser beam casting a shadow that we can measure, and that's shaped exactly like the beam itself.
That's right.
This is mind-blowing. But this laser shadow, is it different from other nonlinear optical effects?
It is. You see, a lot of other nonlinear optical effects, they need very specific conditions.
Okay.
Like precise wavelengths of light, or you need to really carefully control the temperature. But this laser shadow effect,
Yes.
It's actually pretty simple and it's versatile.
What do you mean?
Well, it works across a broad range of wavelengths, so it's not limited to just very specific lasers. It also means it could be used for lots of different applications.
Oh, that's interesting. So it's not just a one-trick pony. It's got potential, right?
Yeah, tons of potential. The fact that we can create a shadow using light itself just opens up a ton of possibilities. Imagine, like, new types of optical switching, controllable shades, maybe even super advanced lithography techniques.
Okay, now this is where it gets really interesting. What would some of these applications actually look like in the real world? Can you give us some examples?
Sure. So imagine using light itself to create incredibly precise patterns.
Okay.
You'd essentially be drawing with shadows. This could completely revolutionize lithography. You know, the process they use to create those tiny circuits in our computers and smartphones.
Yeah, I've heard of it.
It could lead to even more powerful and faster devices.
So from lasers making shadows to supercharging our gadgets, what else?
Think about our optical communication systems. We rely heavily on fiber optic cables to transmit information really quickly.
Yeah.
But imagine using light itself to control the flow of light within those cables. That would mean even faster, more efficient communication networks.
Fiber optic cables on warp speed. Love it.
Exactly.
What other possibilities can you see?
Well, this discovery could even change things in medical imaging. Because of the ability to manipulate light so precisely, we could get clearer, more detailed pictures inside the human body.
Wow, we're talking about a total paradigm shift in how we understand and use light. And to think it all started with this seemingly impossible question. Can light cast its own shadow?
And that's the beauty of science. Sometimes the most amazing discoveries come from asking those really basic questions and daring to challenge what we think we know.
So it's not just a cool science discovery. It's a reminder that we should always stay curious, keep asking why and how. You never know what incredible things are waiting to be discovered.
Absolutely. The world is full of mysteries.
Definitely.
This laser shadow is proof of the amazing power of human curiosity and scientific exploration.
It's clear this discovery could reshape how we understand light and what it can do. It challenges our basic assumptions about what's even possible in the world. But before we get too carried away with all these potential applications, let's go back to the experiment for a minute. Can you walk us through the setup in more detail?
Sure.
Like, how do they actually generate this laser shadow?
Well, the setup was pretty simple considering the huge impact of the results.
Okay.
As we talked about, the key player was the Ruby cube.
Right. The Ruby is the star of the show.
Yeah.
So what about the lasers? What kind of lasers did they use?
Okay, they used two. A green laser with a wavelength of 532 nanometers.
Okay.
And a blue laser with a wavelength of 450 nanometers. The green laser, this was the object that would cast the shadow.
Got it. Green laser, center stage. What did the blue laser do?
The blue laser provided the illumination. Basically, it created the background against which the shadow would be visible.
Okay, so we've got the Ruby cube, green laser shining through it, and the blue laser shining on it from the side. What happens next?
All right, so as that green laser passes through the ruby, it interacts with the ruby atoms and excites them, bumping them up to a higher energy level.
Right.
And once those atoms are all excited, they become much more likely to absorb the blue light.
The blue light that's also passing through.
Exactly. And because this absorption mainly happens in the path of the green laser beam, it ends up creating a dark area, a shadow. And that shadow takes on the exact shape of the green laser.
It's like the green laser is carving out a path of darkness right through the blue light.
Yeah, it is.
So how did they see this shadow? Did they just look at the ruby?
No, they didn't just look at the ruby. They projected the blue light that made it through the ruby onto a screen.
Oh, okay.
Kind of like a movie projector.
Okay.
And on the screen, they could see this clear shadow of the green laser beam.
Wow. So they actually got to see a laser beam's shadow.
They did.
That's pretty mind-blowing. Did they take any pictures?
They did. They took photographs to document the phenomenon. The pictures clearly show a distinct shadow that moves in sync with the green laser, exactly like a normal shadow would.
Okay, so this wasn't just like a fleeting effect. It was a real phenomenon.
Yeah.
That's amazing. But how did they know for sure that it was really a shadow? I mean, were there other tests they could do?
Yeah, they did a few things to rule out any other explanations. For one, they moved the green laser around, and guess what?
Right.
The shadow on the screen moved right along with it.
Okay, so it moved like a shadow. Check.
They also checked if the shadow could be projected onto other objects.
Interesting. How'd they do that?
Well, they put a little marker in the path of the blue light after it went through the ruby. And the shadow of the green laser was clearly visible on the marker, too.
Wow. So this shadow could really interact with the physical world, just like any other shadow.
Exactly.
Okay, that is seriously convincing. They really prove this is a real shadow, even though it's cast by light itself.
It is pretty revolutionary.
It is. But before we get into all the possibilities of this discovery, I've got to admit I'm still a little fuzzy on nonlinear optics.
Okay.
Can you break that down for me again? Maybe with an analogy?
Okay, sure. Imagine you're stretching a rubber band.
Okay.
In a linear world, the harder you pull, the longer it stretches.
Makes sense.
Double the pull, double the stretch.
Okay, that's simple enough.
But in a nonlinear world, things might get a little unpredictable.
How so?
Well, imagine you pull on the rubber band with twice the force. But instead of stretching twice as far, it snaps.
Oh.
Or it changes into a completely different shape.
Okay, that makes sense.
Yeah.
So how did that connect back to the laser shadow?
Okay, so in this case, the green laser is like that force you're putting on the rubber band, and the ruby's response to that laser.
The shadow.
Right, the shadow. That's like the rubber band's behavior. In a linear system, if you double the power of the green laser, you'd expect the shadow to become twice as dark. But in this nonlinear system, that doesn't necessarily happen. You might double the power of the green laser, but the shadow could become way, way darker because the ruby's response isn't straightforward.
So it's like the ruby's reacting in a way we don't completely expect.
Right. And it's because of that nonlinearity that we see these unexpected effects. It's a completely different way to think about how light and matter work together.
This is incredible.
Sure.
It sounds like nonlinear optics is a field full of surprises.
It definitely is. And this laser shadow is just one example of the amazing things that can happen when light interacts with matter in these unexpected nonlinear ways.
Well, I'm hooked.
Yeah.
I can't wait to learn more and see what other weird phenomena are hiding in the world of nonlinear optics.
Oh, there's lots to explore.
And that's what we're going to be doing in the next part of our deep dive. We'll be talking about the possible applications of this laser shadow effect and the challenges and opportunities that come with this whole new area of science.
It should be fascinating.
It should be. Stay tuned.
It is. It really is a fascinating field, full of potential. And it's important to remember that this isn't just about some abstract scientific concept. This could really impact our lives.
Absolutely. We've talked about optical computing, communications, even medical imaging. But could this laser shadow tech actually be used in everyday life anytime soon, like in our homes or workplaces?
It's definitely possible. One thing I can see this tech changing is displays.
Oh, okay. Interesting.
Screens could be brighter, sharper, and use less energy, all thanks to this ability to control light so precisely.
Oh, that would be amazing. No more struggling to see my laptop screen or worrying about my TV using a ton of electricity.
Right.
Are there any other everyday applications you can think of?
Well, imagine things like shades that you can control, or even privacy screens that could be darkened or lightened whenever you want, all using this laser shadow effect. It'd be like painting with shadows. You could create all sorts of patterns or images on surfaces.
That sounds like something right out of a sci-fi movie. We'd be controlling light in our homes and revolutionizing how we see information. The possibilities really do seem endless. But I'm guessing there are some challenges to work out before this stuff becomes a reality.
Yeah, there are definitely some hurdles to overcome. Whenever you're trying to turn scientific discoveries into real tech, there are always challenges. One of the biggest ones here is scalability. I mean, the experiment was done on a super small scale with a tiny ruby cube and these carefully controlled laser beams.
Right. So it's one thing to do it in a lab.
Yeah.
It's a whole other thing to actually build something like a computer chip or a TV screen.
Exactly. Figuring out how to produce these materials on a larger scale and then integrate them into our current technology, that's a big engineering challenge.
Makes sense. What about efficiency? That always seems to be a key factor with new technologies.
Oh, for sure. Efficiency is huge. While optical computing and communications could be much faster and more energy efficient than what we have now, you always lose some energy when light travels through materials.
So even though light travels super fast,
Yep.
it's not always a smooth ride.
Right. It's like, imagine you're sending a package through a delivery system. Even the fastest delivery services run into delays or problems, right?
Yeah.
Well, it's similar with photons, those little packets of light. They can hit obstacles as they move through materials, which leads to a loss of energy and less efficiency.
So it's like a constant race to make sure those photons are moving as smoothly and efficiently as possible so they don't lose any energy along the way.
Exactly. And that's what scientists and engineers are focused on right now. They're working on ways to make optical technologies more practical for everyday use.
So it's like they're trying to build the perfect light superhighway. So what kind of approaches are they taking?
There's a lot of cool stuff happening in materials science and nanotechnology.
Like what?
For instance, they're experimenting with new materials that can transmit light with almost no loss.
Wow.
And they're finding creative ways to structure materials at the nanoscale to control and guide light better.
So it's like physics, engineering, and material science are all teaming up to unlock the full potential of this laser shadow effect.
Yeah, it really is a multidisciplinary effort.
That's awesome.
And that's what makes this so exciting. You have all these brilliant people from different backgrounds working together to figure out a challenge that could completely revolutionize how we interact with the world.
You mentioned earlier that this laser shadow effect is different from other nonlinear optical phenomena. Can you talk about that a bit more? What makes it so special?
So with a lot of those other nonlinear optical effects, you need super specific conditions,
Like what?
very specific wavelengths of light, or carefully controlled temperatures, things like that. But this laser shadow, it's just simpler. It works across a wide range of wavelengths, which means it can be used with many different kinds of lasers.
Okay, so it's not limited to just very specific setups.
Yeah.
It can be adapted, used in different ways.
Exactly. That makes it way more practical for use in technology. Plus, it means it could be integrated into the systems we already have without needing to completely redesign everything.
That's a huge plus. So this laser shadow effect is simple, versatile, and easy to integrate.
Yeah.
Seriously impressive. I think it's important to stop for a second and just acknowledge how big of a deal this discovery is. We're creating shadows with light.
I know, right?
It just changes how we think about light and what it can do.
It definitely challenges our basic understanding.
For sure.
Yeah, it's like we've expanded what light can do. We've found this whole new way for it to interact with the world.
Love it. So speaking of expanding possibilities,
Yeah.
what about quantum information science?
Oh, that's an interesting connection. Quantum information science is all about using those strange rules of the quantum world to create new technologies for computing, communication, even sensing.
Yeah.
And while it's still early days, I think this laser shadow effect could definitely play a role in that field too.
How so? Can you give an example?
Sure. One of the big challenges in quantum information science is being able to control individual photons, those little particles of light.
Right.
And this laser shadow effect, because it can control light so precisely at the atomic level, could give us new tools to manipulate those photons.
So we could potentially use this effect to build the pieces for quantum computers or super secure communication systems.
It's possible. But of course, there's still a lot of research to be done. That's what's so great about this discovery, though. It's not just about what we can do today. It's about the new paths it opens up, the new ways of thinking about light and what it might be capable of.
It's like this discovery has given us a brand new way of looking at the universe.
It really has. And you never know what other amazing breakthroughs are out there waiting to be found.
It's just incredible to think about all the ripple effects this discovery might have. how it could change our future in ways we can't even imagine yet.
It really is. It just proves how powerful human curiosity is and how much we crave understanding the world around us. I mean, who would have thought that such a basic question?
Can light cast its own shadow?
Right. Who would have thought that could lead to such a big change in how we understand light and what it can do?
It really highlights that the universe is full of surprises and that asking fundamental questions can lead to truly groundbreaking discoveries.
Exactly. And it reminds us that the journey of science is never really over. There's always something more to learn, more to discover, more to be amazed by.
This has been such an amazing conversation so far. We've talked about some seriously mind-bending ideas, but before we wrap up, I want to bring things back down to earth for a moment. We've talked a lot about the technology, but what does this laser shadow effect really tell us about light itself and how we relate to it?
That's a really good question. I think at the most basic level, this discovery makes us rethink the whole idea of light and dark. We tend to think of light as the thing that illuminates, that shows us things. And we think of darkness as something that hides things.
Right.
But this laser shadow shows us that light can also create darkness. It can be both.
It's like a yin and yang of light.
Exactly. I think this has big implications, not just for science, but for art, philosophy, even how we understand ourselves.
How so?
Well, we use light and shadow as metaphors all the time to make sense of the world and our place in it. This discovery makes us look at those metaphors in a new way. It makes us think about the complexity of light and darkness.
It's like this laser shadow has shined a light on how we understand light itself.
I like that.
It's showing us that there's so much more to discover.
It is. It reminds us that the universe is full of wonder. Even the simplest things can hold secrets we haven't uncovered yet. And it just shows the power of the human mind to dig into those mysteries and unlock those hidden wonders.
I feel like we've just scratched the surface here. I'm excited to see what new discoveries and technologies come out of this in the years to come.
Me too. It's a really exciting time to be involved in this field. I have no doubt we'll see even more amazing discoveries.
I can't wait. Well, we're going to wrap up this part of our deep dive here, but stay tuned for the final part. We'll be going even deeper into the potential of this laser shadow effect.
It's going to be good.
We'll also talk about the ethical and societal implications of this groundbreaking discovery. You don't want to miss it. Welcome back to the deep dive. We've been on quite a journey exploring this mind-blowing world of laser shadows. This discovery has really challenged how we think about light and opened up so many possibilities.
It's been amazing. From those tiny details of the experiment to the massive potential in fields like computing, communication, even quantum tech, it's been mind-blowing.
It really has. But before we wrap things up, I think it's important to talk about the bigger implications of all this. We've covered the potential benefits, but what about the possible downsides? Are there ethical or societal concerns we need to be thinking about?
That's a great point. Like with any powerful technology, there's always a chance for misuse. We have to be careful and really think about the ethical side of this discovery as it moves from the lab into the real world.
What kind of concerns are we talking about specifically? Where do we need to be extra cautious?
Well, one area that jumps out is privacy. If we can control light so precisely, it makes you wonder about things like surveillance. Could this tech be used for invisible tracking or monitoring? Imagine a world where cameras could see around corners or right through walls.
That's a pretty scary thought. Kind of like a dystopian sci-fi movie. Are there any rules or regulations in place to stop that from happening?
It's early days yet, but we definitely need to start talking about these things now as the tech develops. We need to make sure the right regulations are in place to protect people's privacy and prevent this tech from being used for bad things, like surveillance.
It's a good reminder that scientific progress always needs to consider ethics. We can't just think about what we can do, but also what we should do.
Exactly. And it's not just about stopping negative things from happening. We also need to make sure everyone benefits from this tech. We need to watch out for biases that might be built into algorithms or systems that use this laser shadow effect, and we need to make sure everyone has fair access to these advancements.
So it's not just about the science, it's about how we use it in society. We need to make sure it's used for good, not harm.
Right. It's about shaping the future we want to create, a future that's good for everyone, not just a few people.
It's a reminder that we all have a role to play in how tech develops. We have to stay informed, be part of the conversation, and push for responsible innovation that reflects our values.
I completely agree. We need to work together to make sure these advancements are used to create a better, more equitable future for all.
Well said. Well, folks, it's time to wrap up our deep dive into the world of laser shadows. It's been a wild ride full of amazing science, mind-blowing possibilities, and really big questions about the future.
It has been incredible. I've really enjoyed getting to explore this topic with you and share what we've learned with everyone listening.
Thanks so much for joining us on this deep dive. Your expertise and insights have been invaluable in helping us understand this incredible discovery. And to our listeners, thank you for tuning in and engaging with us on this mind-blowing topic.
It's been my pleasure. Remember, the journey of discovery never really ends. Keep asking questions, keep exploring, and don't be afraid to challenge what you think you know.
Couldn't have said it better myself. Until next time, keep those minds curious, stay engaged with science, and never stop asking those big questions. Who knows what incredible discoveries are waiting just around the corner?